Coming up in this video, I'm going to take this Rubidium Frequency Standard, something I looked at last time. It's fantastic. It's a really good thing. You see them, you think, yep, got to have one. The problem is that. I mean, it's all a bit hard. You have to wire it up and do stuff with it, and it gets really hot, and so it really, it's a component. It is a nice little metal box, but it's a component. So what I'm going to try and do in this video is I'm going to encapsulate this. I'm going to turn this into something that is practical, useful in the lab, won't get in the way, won't have bits of wires hanging out of it, and actually will serve a purpose. Now, to do that, there's a whole series of things we have to do, and I'm going to try and do that all in one video. So I'm going to do the whole thing this afternoon. I'm going to try and get it done in a couple of hours, end to end, so there's a lot to cover. We're going to cover everything from finding the right enclosure, planning the layout and the construction, how's it going to fit into the enclosure, what it's going to look like, what the rest of the enclosure will be. We're going to look at thermal management. These things get really, really, really hot. All right, so we want to make sure that we don't cook it, and we don't want to cook the other things that are going to be in the enclosure, like the power supply. So we're going to look at the thermal management. We're going to look at the actual metalwork, physical construction, drilling holes and what it is and how we're going to adapt the case or get the case to work. We're going to have a look at a little bit of video line transmission theory and some practical use of that, because it just so happens that the enclosure I've found is related to video, and we'll take a look at that soon. We're going to have a look at the status indicator. This thing powers up. It's not ready to use when you switch it on. It takes time. It has to warm up, and then you have to use it. So we're going to look at status indication to make that useful. Now, to make the status indicator work, we need a little small microcontroller. So we're going to look at a little bit of software. We're going to write some firmware, really simple, get that working, get that as part of it, and then eventually bring everything together into a made working final unit. My aim is to get this done, literally, as I said, in a couple of hours. So let's go. Okay, so I don't know about you, but the first thing that I ever get when I build a project or work on a project is, do I want to put it into use, or do I want to build it to learn and then put it away? If I build it to learn and put it away, I'll build it on a board, a variable board, or whatever it is, and I'll put it away. But if I want to put it into use, if I want to make it reusable and essentially encapsulate and capture that learning into something that actually has a practical use at the end of it, then number one on the list is enclosure. Where do you get an enclosure? So you go to Farnell, you go to all the distributors, you trawl the websites, you get to know the various enclosures. It's a really hard thing, and you know what? Never normally do you find an ideal enclosure. It's always hard work to get that match. And this Rubidium Frequency Standard has a unique need. It's going to get hot, so it can't really be plastic. Can't put this into an ABS box. Actually, in my lab here, I've got various bits of equipment that take a 10 megahertz input. So actually, ideally, I'd like this to feed more than one instrument. I'd like it to be something that could be sat on the shelf and not cause, not to be too much of an eyesore, and certainly don't want it looking like it's been sort of made out of a bird's nest. So now, unfortunately, I failed miserably to find an enclosure, and so I'd set the project aside and just left it. And fortunately for me, someone contacted me on my blog and said, you know what, go have a look at this eBay item, you might find this interesting. So off I went, and I did, and I found this. In fact, I didn't find this. Andy found this, and he pointed me at this. And this is a really nice aluminium enclosure. It's nice and robust. It's it's good construction, I think. But what's really good about this is what its previous purpose was. It is in fact a video distribution system. So the way this works is it distributes high definition video. So you put in RGB and sync here. I won't talk about the bottom row here for a second, as best I can tell. RGB and sync, these are analog signals, that's a digital signal. And then out of these three here and these three here come not amplified but buffered versions of that signal. So this is typically used where you would have an airport lobby where you've got loads of monitors around the place. You'll feed your master signal in here. You can connect up to 6 monitors. Now, there's something really good about that. It being video amplifier, it's probably got bandwidth that's good for 50, 60 megahertz. It's high definition video. Now, and it's analog. That makes it an ideal piece of electronics to distribute my 10 megahertz signal. So in theory, if I put 10 megahertz in here, I should get 10 megahertz out of each one of these, and we'll try that in a second. So this is a great thing to adapt. Now, that aside, the fact that it's got that in there is one thing. Now, video signals in this case happen to be 75 ohms, and we'll get onto that later when we talk about oh God, mental block, when we talk about the transmission lines for video. Thank you. And we'll come back to that, because obviously 75 ohms is not quite what we want. What we need is 50 ohms, so it's slightly different, and I'm sure we can adapt that. But the other characteristics of that, ready-made power connector, great, ready-made metalwork, we don't have to do too much to this. It's got a power light, that's great, that's good. That might serve as our power light and our status light. No power switch, so that would have to be added. It's a solid construction. Let's I think what we need to do, first thing, when I got this, the first thing I done was I took the lid off and had a look to see, can I fit the Rubidium Standard into here, and what does the electronics in here look like? Is it something we can use and make use of? So let's start now and take this apart and have a quick look inside. Okay, so the first thing power supply here. That's looks like a fairly small power supply. We'll get into that in a second. And we've got what looks like a big PCB. There we go. Let me just take off this cable tie and unplug this. All right, so let's have a look. So obviously we've got power supply. If you look at the construction of this case, it's solid aluminium. I noticed there's some standoffs. They probably look like rivets, I think. There. Now let's have a look at the back of here. So if you just disconnect these cables. Okay. All right, so the first thing to do, I guess, is look at this and assess this for suitability. As I said, these are the inputs here, and these are the outputs. So if we have a look at the circuitry here, let's see if I can get around this way. I can try and point this out. So these are the input signals here. They look like they're feeding both of these op amps here, and there's obviously 1 per 3 connectors, so there's 3 connectors and it's op amp, 3 connecting, there's 3 channels RGB. The 4th channel has got some TTL logic down here, so that would add up, because this is actually H or HV sync, so this is a kind of TTL level sync. In fact here 1 volt or 4 volts is what it says here, so there's actually switchable gain. And there's also switches on here to AC couple or DC couple the input signals to the op amp, so that's quite interesting to maintain DC levels or relative AC levels. And this bottom row here is also HV. So this is a vertical sync. So this is an additional. And this is actually a separate board here, so probably for my purposes I don't think we'll need that board, so I'll probably remove that board and get down. So let's take some measurements around here, and perhaps we'll talk a little bit about I'm going to identify this component, and we'll figure out what that is, and then we'll talk a little bit about how this might work, and how we might adapt it for our purposes. Okay, given it's basically a complete unit, I think what I'm going to do first is power this up and then see if I can feed a signal in. And sorry about the creaking chair here. So what I've got a SIGGEN here running at 10 megahertz. So I'm just going to, and that's running at 1 volt peak to peak, which is fairly representative of a. There you go, so there's a 10 meg signal. So now, although there's going to be an impedance mismatch, what I'm going to try and do is run this through the video amplifier. So I'm just going to take this cable, which is coming from the SIGGEN, and feed that into one of the inputs. I'll bring the camera down on this in a second, and then take a second cable. Where are we? Take a second cable here and take this into one of the outputs. I'll keep the camera on the scope just for now, just so we can. and take that into one of the outputs here. Get some power on this. Okay, so there we can see we've got some output there. That's coming on the spin that around there. That's on one of the outputs. So I'm just going to test the top 6 outputs. Make sure that that's third output, fourth, fifth, sixth. Okay, so there's the outputs there, and I'm just going to flick the AC and DC. So that's in AC mode. You can see it's playing havoc with my trigger level here. That's in AC mode. That's in DC mode. AC mode again. Okay, so there's a slight DC isolation or DC offset there. All right, so to me that looks pretty good. I'm going to try the same. I'm just going to feed this signal into the H sync, which probably won't work. Let's see what we get out of that, which is the digital one. There's the digital signal. So I don't think my transmission lines, this is a 50 ohm termination actually. Let's see if we can, not sure if we can change that on this scope. There we go. Let's just bring that down to a more respectable horizontal frequency. Don't know what it is, but let's have a look at that. Okay, so that's a fairly clean sine wave, square wave. Okay, so this is quite interesting. So it's working. That was the square wave input there. I've got no use for the second row, but my initial thoughts here in terms of planning, assuming we can get everything into this enclosure, I think what will be really good, we can make some adaptations to this, and we'll come on to the transmission lines in a second. But in pure practical terms, for not wanting to waste, what I know I've got on the Rubidium frequency standard is I've got the 10 megahertz reference signal out, and I've got a 1 pulse per second. So I think what I'm going to do is remove these 3. Well, I'll remove all the inputs connectors because we don't need them. And the AC-DC coupling, we don't need that either because we're not going to put anything in here. And I think I'll wire this, or we'll reconfigure this to get 10 megahertz coming out of the 18 connectors, the 18 RGB connectors. So that gives me up to 18 devices I can plug in, all nicely buffered. And we know that actually each row of 3 is buffered separately. So if I want to use it, having complete separate buffers, then obviously I can use one per channel effectively. I think I'm going to bring out on the bottom 6, or the H/HV sync, I'm going to bring out the 1 pulse per second. So that'll be that, and then this bottom row we know is on a separate board, so I'm going to get rid of that as well. So let's now look at the theory of the transmission lines, because as I said, these are actually 75 ohms, and we're going to need to make some adaptations to that. So let's have a quick look at the theory behind that, and then we can have a look at the electronics on this board to see how we can adapt it. Okay, quick drawing of what's going on inside there. So first of all, I've looked up the op-amp. It's a CLC 409, which is actually a Texas Instrument part. It's obsolete now, but it's 350 megahertz, very high bandwidth op-amp. I've drawn what I believe is the basic circuit. I'm sure there'll be more to this, but this is essentially what we're looking at. So in each one of the 3 channels, we've got red, green and blue channels, if you remember. We've got an input connector, we've got an AC-DC switch, which will be just shorting out capacitor as the input. Then we've got, in fact, that switch and that capacitor might be the other side of this 75 ohm resistor. In fact, it almost certainly will. So please bear that in mind. That's probably a mistake. But we've got basically a 75 ohm resistor. So that's providing the basic input impedance of 75 ohms. And then that's driving into the positive of the op-amp, which drives the 3 outputs of the given channel. Now, bear in mind that there's 2 lots of 3 outputs for each of the red, green and blue, if you recall. So there's one input shared between 2 amps effectively, so there'll be a second channel that looks exactly like this up here, and this will be the feed point to that. There won't be a second 75 ohm resistor, so that's part of the input. Now, obviously there's a simple gain setting network here, which may well be compensated. I haven't tried to reverse engineer the board because I know it's working and we don't need to change it. And then the output of this op-amp is a very, very low impedance source. So in order to get the right impedance for our transmission line, and a transmission line in very basic terms, a BNC socket, a coaxial cable, another BNC socket on the target equipment. The target equipment will have a terminator. Obviously, if it's 75 ohms, it'll have a 75 ohm resistor in it. And the way these are wired, the transmitter, the sender, will have a low impedance amplifier source, and that will go through a 75 ohm resistor. So unlike the input, which is a load effectively on the transmission line, the output is driven through a resistor. The idea here being that when you take when you complete the circuit here, you'll effectively get half the amplitude here than you will here, and that's very normal. Now, because this is a low input, that's how typically our transmission line is set up. So because we know that this is a low impedance source, and we know that one op-amp is driving three outputs, the three outputs will be wired like this. There'll be a separate 75 ohm resistor for each of the three outputs here, giving each one an impedance of 75 ohms. So to adapt this for our purposes is really straightforward. I don't think we have to do anything other than, well, we're going to modify the input, because I've basically on the board there's an R, a G and a B input. There's a red, green and blue input. So we've got to basically drive our 10 megahertz signal coming out of the Rubidium Frequency Standard into all three inputs. So we've got to parallel effectively the input to 6 op amps. And even though there's a terminator on each of the three channels, we've got to basically remove all of those except for one, and we've got to change that value from 75 ohms to 50 ohms. So what we want to end up with is an input. We'll get rid of this probably because we don't need it. We're connecting internally, so all that can go. So we'll have a single 50 ohm load resistor on the input, and that will connect to all 6 op amp inputs. So that's the change there. And then on the output, really all we have to do is replace these 75 ohm resistors for 50 ohm resistors. It's really as simple as that, and then there's no reason why that circuit won't work and also be nicely impedance matched at 50 ohms. So I'm going to go, that's there. What I'm going to do now, this is powered down. I won't bother keeping the video on for doing this because it's all a bit boring, but what I'm going to do is I'm going to strip this down. I'm going to take all these nuts off because it all looks like it's held together just by that, so that should be relatively straightforward. I'm going to strip this down, take these boards out, get this board off. Now, actually, there's one thing we ought to do just before, while it's in its current working state, before we get too carried away. One of the things I do need to know, let's get rid of that. I suspect it doesn't need that. We do need to know what the power supply, it needs to operate. So let's just get one of these meters here. Let's have a look at the DC voltage. And the reason why I say that is I'm almost 100% confident that this power supply will not be enough to drive the Rubidium. It's probably not the right voltage either. But anyway, let's just check those things out and see where we end up. I'm sure this is. Need to connect the power supply as well. Okay, so we're powered up. Let's tape it. So the colours here, we've got red, black and orange, so I'm going to take a wild stab in the dark and guess that black is 0 volts and red is plus volts. So the red is reading, let me just zoom out here a second. Okay, so on between black and red I've got 6.7 volts, and between black and orange I've got 15 or 16 volts. Okay, that's curious. Let's just have a quick look at the data sheet, which I've got. So I've just leant over to the computer here so I can see the data sheet. And pin 7 and pin 4 are our connectors. So I'm going to take my common point, our power. I'm just going to have a look and see. So pin 4 Can't read anything on here. Okay, so pin 4 has got minus 4.9, so minus 5 volts on it. And pin 7 has got plus 4 volts, so that's interesting. So this board is somehow generating a plus and minus supply from 2 positive supplies. So let's have a quick look at that, see how that works. Okay, well, what I'll do, I'll take this apart and then we'll have a closer look at the power supply circuitry, but that's effectively it. So the goal is to strip this down. Oh, there's one other thing we probably ought to check while we're here. Just make sure that the theory that I've put down here actually adds up, makes some sense. If I just get this here. Okay, so we see that I said that the input must be terminated with 75 ohms, so let's have a look at one of the inputs. Again, I'm pretty confident we've got a good ground, a good common here. So each one of these inputs, so these are the middle 3 here, and the input impedance, there you go, 75 ohms on each one of those. And if I trace that circuitry here, that looks like our terminating resistor here, and this is feeding then into both op amps. Let's just have a quick look here. 1 second. Where are we? In fact, that's going to this switch here. There. And it's about 200 ohms then going into the input of the op amp. Okay, so the input termination there, so I'd expect to find 3 of those resistors here. Which would appear to be there. That one is also a terminating resistor by the looks of it. 75 ohms, yeah, so we've got 3 input terminating resistors, 1 for each of the 3 channels, and that terminating resistor is shared by both sides because those particular ones aren't repeated over here. Then on the output, we've got the output of the op amp, which is on pin 6, and this is repeated for each one of these. It's coming along this bus here, and you can see that there's 3 resistors, each then going to the output pin of the respective B and C. So if I take a measurement from, if I come onto the pin 6 of the op amp, which is its output pin, and go to the output pin on each of the 3 outputs, we've got 75 ohms, 75 ohms, and 75 ohms. Hopefully. Yeah, there we go. Okay, so that's sort of basic confirmation. So in summary, what do we know about this? We put +5 and +15 on here. This is an LED which lights up to show it's got power. We don't need this extra board, so we can ignore that for now. And we know that we've got 75 ohms on the input, and we've got 75 ohms output resistance for each output. So the modifications I need to make for this, apart from looking at the power supply to learn a bit more about it, which we'll do when we take this apart or take this board out, is I've got to replace each one of these output terminating resistors, output resistors 75 ohms back to 50 ohms. And I suspect I don't have any 75 ohms. I'll certainly have 100 ohm resistors, so I'll just put 2 on top of each one. We're going to remove the input sockets from the centre, and we've got to get a bit of coax on here, or get something on here, and make sure these are all wired in parallel. So all 6 inputs are paralleled up with one single 75 ohm termination, and again, because I don't have 75 ohms, I'll have to use a pair of 100 ohm resistors. Alright, so I won't bother videoing taking this apart because I think that would just be boring for everyone. So I'll go and take this apart now, and I think I'll just do that modification. I'm sure nobody wants to see me solder some resistors, so let me do that, and then I'll come right back. Okay, so first off, I've removed that. That's the bottom board. If you remember, there was 2 boards. This is the kind of bottom board on here. I just don't need this, so I'll probably just, I'm not sure I'll even bother keeping these sockets, but anyway, it's got a couple of 7.4 buffer chips on there, and an LT 1016. I think that's some kind of comparator, so fast comparator for shaping the input. Anyway, that's that. We don't need that, so that can go over in the junk pile. I've modified this board now, so I've I've taken off the 4 input sockets. I've replaced each one of the resistors here. Let's see if I can get some focus on here. I don't know if that's going to focus that well. There you go. And basically I was right, I didn't have any 50 ohm resistors, so I've just put 200 ohm resistors on top of each other for each input. I've also taken a bit of this very nice Teflon 50 ohm cable, and I've soldered that in at this location here. I've linked the 3 inputs, so we've got all 3 inputs in parallel, and I've removed all of the termination resistors except for 2, which is 100 ohms each, so that gives me a 50 ohm input impedance, and I've removed the 3 switches that we used for setting up the AC or DC, because we didn't need any of that. So that's nice simple modification. So that board should be ready to go. So that's the first thing. I'll put that aside. The next thing is, of course, remove all these, remove all this lot, and then what do we do? Well, I think that's a nice simple solution there, is to take the back plate and put some blanking plates in there, some BNC blanking plates. So obviously remove the bottom board, blanked off those, remove the 4 inputs, blanked off those. Now if I was doing this properly, really what I ought to do is sand this down, prepare it, and relabel it, but you know, I'm not planning to sell this or do anything with it. I'm just going to stick it on my shelf. So I think that's stick it on my shelf and actually use it. So that's a nice simple, fairly self-contained board. Let's just get that on there. Once the nuts are on there, obviously the power socket will go back in there, and we're ready to go. So, okay, so that's that bit modified. Okay, so the next thing is to think about power, because we know that this power supply really isn't going to be up to the job, and we know we've got to we run this at 15 volts at least an amp and a half. So I had a quick look around on eBay and found this this power supply. In fact, this was pointed out to me as well, but this is quite a nice TDK lambda power supply. It's 0 to 50, it's 15 volts at I think the spec is 2 amps, 2.4 amps in fact. There we go. Hopefully we can get some focus on that. There we go. 15 volts at 2.4 amps. So perfect, really quite small, quite compact. So let's, the next thing to do really is, in considering trying to do something like this, is you really want to have a clear idea of how you're going to lay this thing out. How's it going to work, and how is the everything going to fit in. Now we know, first of all, that we've got some limitations here in terms of room. So this is going to have to be in the back here. We've got that kind of space there. Now the 2 things we've got to get in here, well, there's 3 things we need to consider. The first thing is we've got to power it. We've got to get the rubidium in there. That's the whole point of doing it in the first place. We probably need some other ancillary bits and pieces like this power supply to generate the 5 volts that this thing needs. We know that that this front end also needs 5 volts and plus 15 volts, and we'll look at that in a second because we said we'd talk about the power. So we've got to get that in there. And the thing that really worries me about this, and I think this is the main concern I have, is any switch mode power supplies are notorious for failing if they get too hot, because the electrolytics dry out and all the rest of it. Now clearly what we're about to do is put a switch mode power supply into a closed metal box somehow like that, and a something that runs at 100 degrees C plus. In a closed metal box, and we're going to generate lots of heat, and that's just clearly not going to be good for the electronics. So the other thing that needs to happen, well, what I would really like to see, is get some air movement in here, and that's going to mean a fan, which is a bit regrettable. But we need to aim for a fan that's going to give us enough air movement to keep just to keep it moving, and not let the heat settle too much. This box is going to get hot. That's it. There's no 2 ways about it. So so it's important that when we try and work out how to put all this lot together, is that we consider the thermal characteristics of how this might work. Now I'm just removing this this back for a second. The other problem with this case is it's got these standoffs here, which, from the best I can tell, are actually riveted because they're invisible here. So any attempt to remove those is almost certainly going to damage the case. So we've got to leave that in there. And also we know that the power socket is at the back here. So we've got to give some reasonable consideration to layout. Here's the power socket here, and our front panel, the power light's over here. Sorry, the power light's over here. So I probably need to put a power switch over here, and we'll get that together in a second. But the main thing is to work out what the layout's going to look like. So, you know, I had a bit of a play around with this already. You can see that things are pretty tight. That standoff's in the way. I can't quite get that in there. I can't get that to sit flush. This is all pretty tight. I certainly don't want to do that, you know, because I could mount this to the top and mount that to the bottom. It is possible to actually mount this to the top. That's certainly an option. Now, why wouldn't I want to do that? Well, if I want to stand other equipment up on top of this, first of all, apart from the fact that this also got these 4 standoffs, and it's not you know, it's not going to be easy to remove them. So there is no real place to put it either. It's just not going to fit. You see, it bumps into these standoffs, so that's not going to fit on there. And I'd like to try and get rid of some of the heat from this as well. So all of those things considered, where I get left with is probably, and it only just fits, but fitting this to the front panel seems to be the way to go. So if that's there, fit it to the front panel. That can fit nice and snugly. The power supply ought to fit here. Now, why would I turn it that way? Well, first of all, the mains is over here, so I've got the connectors here. I do want to create as much space as I can between here and here, and also that back plate is solid, so any radiated heat, infrared heat, should be nicely reflected by that silver surface. And the only thing I now need, so assuming that can lay in there, and this can slide in here, just to make sure that all lines up. The only thing I now need to worry about is airflow. So I'm going to reposition the camera, and we can talk a little bit about airflow and see where that leaves us. Okay, so if this is our layout here, then the only obvious thing to do, I've got a fan here, an 80mm fan, and as luck would have it, it does actually very snugly fit right in between those 2 standoffs there. So without having to remove those standoffs, I can get that fan in like that. Now, the goal will be to, if you look at this layout here, will be to get air to be drawn in from the bottom, and you know, the bottom of this does have legs. So if we look here, it's got legs, so there's a gap here. Air to be drawn in from the bottom and pushed through here, and ideally I want air to be flowing. Obviously this is going to be a lid, so it won't come out the top. It'll be forced to flow across. Well, flow across wherever we decide, because what we need to do is cut some vent holes. So what I'm thinking is I'll have that in there. Air will be forced through here. The back is blocked off effectively, and then I'll cut some vent holes here, which don't have to be anything too complicated, but I'll cut some vent holes through this section here to ensure that air is blown across, or you know, air movement is moved across this power supply through this vented side of the power supply, and out this side here, and also take away any air, any warm air that's in here. Just get that movement. And then as a secondary thing, I think what I'll also do is mount a heatsink on the front here, and thermally couple the rubidium to the heatsink to the front panel, so the whole thing is as best I can dissipating heat at the front. So when it's up on a shelf like that, you know, a lot of the heat is coming out the front. So that's the basic plan. So the fundamental things I need to do right now is mark this up and get a nice hole cut for the fan. I did get this on eBay for a couple of quid, and it's effectively a fan grill. So I envisage that'll be at the bottom of the placed on the bottom once I've cut the hole. The fan will be fixed then. We'll drill some holes along here. And that should be ready to go. Now the next thing is this. So that's the mechanical construction. Actually, as long as I don't have to fit anything else in there, that'll be basically that should be a fairly reasonable physical construction. This thing here, if you remember, we said that it takes +5 and +15 volts. Well, that's actually quite convenient because, as it happens, this also takes +5. This rubidium also takes +5 and +15 volts. And if you recall from my previous video, I actually used this thing to generate the +15 volts. So probably what I'll do, I haven't really looked at how feasible this is going to be, but I'll probably work it out so I can just mount this thing on here somehow by, you know, just soldering the ground to, I don't know, one of the ground points or one of the earth points here, just so it's physically mounted to this, so it's not floating around in the. Don't know how practical that be. We'll see. But the other thing to note on here is the power supply in here seems to have some kind of switching supply, and in fact, it's got a linear technologies DC to DC converter chip here. And what's happening is the 5 volts, the 6.7 volts is being fed into a 7805, which is being regulated down to the 5 volt, positive 5 volt. And the switching converter is actually generating a negative voltage from the positive voltage, and that's being fed into a 7905, generating the -5 volts. So this circuit is actually being powered off a plus or minus 5 volts. But I don't think there's any need to change this. I think we can work with that. What I need to do is just check that by using this arrangement we can power it off of 15 volts and get a reasonable quality output. If we can use the same power supply to power both this preamp board and the Rubidium Standard. Okay, so one other thing we need to think of or consider here now is when these Rubidium Standards powered up first, they're not ready to be used, and I wanted some kind of visual indication. So the easiest way will be to drill another hole, put a second light in, or a second LED, have one for the power, or even just use this one. So it only comes on when it's ready. The problem with that is when you power it on and nothing happens on the front, it's confusing. So I thought what we do for this exercise, I think it's something we can knock out really quickly, is I'm going to use one of these, which is a PIC 12F675 microcontroller. It's a simple 8-pin device with no external components, perhaps just a decoupler and a little bit of software. I'm pretty sure we can knock up a simple LED handling chip that will, when you first power it up, it will blink this LED so you can see it's warming up, and once the rubidium indicates that that it's ready, it will set the light on solid. So that's a really simple thing. Again, not sure how I'll mount this. I'll either probably just put it on a very small bit of prototyping board somewhere. Let's have a look. Got something over here. Can't quite grab my hands, I can't quite pick up something, but yeah, it's a small bit of prototyping board. And again, I'll mount it in a similar way on the back of the preamp, probably to the small power supply. So that's the next thing. So I think the next thing to do now is I'm going to go and do the metalwork for this. I'm not sure if I'll put anything on camera. I'm not sure it'll be that exciting, but I'm going to go away and you know, the main step here now is to make sure we've got a good physical and workable physical construction. One thing I don't have to hand, unfortunately, is a heatsink. So I'm going to aim to do it. I said I wanted to finish this all this afternoon. So I'm just going to aim to build this without putting the heatsink on the front, and then I can get to putting that on later on. Okay, I'm not trying to be precise here, but I want to make sure that that I get this reasonably well organised, because I want to make sure this all hangs together nice and cleanly. So I'm limited for space because of these spacers here, and so what I'm going to do to get those markers, I've just found this bracket which is off a Keithley meter. It's given me about a 10mm spacing. I want it to be square and flush, so I'm just pushing that in there and push the fan up. So that's my location. Now all I'm going to do to mark this fan is I'm going to put 4 very, very simple or very, very basic pilot markings in there. I'm not trying to be that precise, so anyone that's going to call me out on this, feel free, but I'm not going to ignore it. Basically, I'm just going to 4 approximated centres in there, and with those 4 markings now, I'm simply going to use a straight edge, and I'm going to draw a line across the 2 corners. That'll give me a centre point. Now I'm going to get this bolted onto the drill press and put an 80mm hole straight in there. Okay, this is these are classic circular cutters. They're really used for, they can cut aluminium, there's no problem. You can see that I've used this quite a lot for kind of building work, cutting holes in drywalls or ceilings for spotlights, that sort of thing. But it's be perfectly fine to cut this. The problem with these is they do tend to move around a bit, so a good solid drill press is really helpful, and you should get quite a clean cut if I take my time and lubricate it. The way these cutters work, you've got different sizes. This is 79mm. Now it'll cut a 79mm hole, and it'll probably that should be perfectly adequate for what we need here. It's pretty close. It certainly doesn't go over. And the way these work is you just screw these in. You don't tighten them up. You just get them aligned here, and then this outer one basically pushes pins into the thing, so you get a tight fit. Right, let's get it on the drill and get it. Okay, that's mounted on there now. I did unfortunately I got a bit of lateral movement when I was drilling it. I couldn't really clamp it, so I got a little bit of overbore. You can see it's a couple of millimeters over, but it's or about a millimeter each side over, in fact, or maybe slightly less. But anyway, it's perfectly fine for this. Just running the fan there at 6 volts. It's very quiet. Really can't hear it. I'm getting enough air movement, so I think that'll be good enough. So that's the fan mounted in there. Okay, so power supply is fixed in there. This is the front panel, and I think what I'm going to do, because I've got a power light over here, and I'm going to put a hole in here for a power switch, a toggle switch, and on the actual case, the power connector is here. So what I think I'm going to do is invert this there, which is okay. So I get the same effect now. That means I can repaint this, and I've got it, as I said before, I've got a heatsink on order, which I need to get, so I can mount over here. Got the LED here for the power light, and I can put the power switch here, so it makes better use of the space. So the Rubidium Frequency Standard is going to get mounted in the back here against this front panel. It just about fits. So all right, so yeah, I think that's what I'll do with that. You can see the power supply is mounted now, and let's just have a quick double check, make sure everything fits exactly as we would like it to. There we go. So that looks pretty good to me. I think everything seems to be as we need it. The side panels of this are made up of, I think originally this case was designed to have 2 different heights, and they've put a filler piece in here which holds the front and the front panel here. So what I'm going to do is I'm going to drill this to get the vents for the airflow coming out of the right hand side of the unit. So I'll go and do that next, and then I think pretty much all the heavy lifting is that, and I'm going to mount a front panel switch here. So once that's done, all of the heavy lifting is over. Okay, so here's the front panel drilled. I've put a switch, simple toggle switch. I've chosen that kind of switch simply because I can drill a hole. I've got a drill with the right size, easy enough to cut a hole in there and mount the switch. LEDs back in there, but this way, and the frequency standard is mounted on the front with 4 bolts. And I've put the rear panel back on. Also, let's just have a look, make sure. So the basic mechanical construction. Sound, get a nice little bit of clearance there for those bolts at the top and bottom. I haven't yet removed the power supply, so I think that's a good physical layout. Everything seems to fit in place nicely. Yeah, that's all good. Can't put this on just yet. Let's just remove this power supply. Okay, that's great. Obviously we've got to drill this now and create the vent holes for that, for the airflow. Okay, so I've drilled this, it goes around that way, and this gives me just 4 holes. It's not great, but what I'll probably do is I'll find some suitable meshing material, fine meshing material, and then I'll sandwich it in between here and here, just to stop any screws or anything big from being dropped in there. But I think that'll do for now. So the heavy lifting as far as the mechanical construction is done. Next thing to do is to look at how I integrate all this. Obviously I've got to connect the fan, got to make a small PCB for the microcontroller, got to get the various, get the D connector here wired up properly with some wiring, basically make a wiring loom and plan that out. So that's the next thing. I'm going to go and find I think what I'll aim to do, not quite sure, but I think what I'll aim to do is put a small prototype PCB in here just to mount all the other bits and pieces on. I'll go and have a look now, and I'll come back on camera once I've figured out how I'm going to construct that part of it and talk you through it. Okay, so to get all the connectivity, I was thinking about mounting a board on there, but it's going to be really awkward running all the various cables and connectors up there, so I'd rather have the top removable. So I think what I'll do, because I've mounted the power supply vertically in here, there are 2 mounting screws on the back of the power supply here, M3 screw fixings just here. So I think what I'll do is I'll cut this board down a little bit, and I'll just mount that directly on the back of the power supply on standoffs, and then all of the wiring for this lot. The goal here then is all of the wiring can all be brought to this point. The microcontroller can go on here. These boards can be just mounted on hard wires, just raised above, and then the whole thing can be wired up in prototype form. So I think that's the way to go. So what I'm going to do now is I'm going to go and cut this thing and get it to size, get a couple of holes drilled, and then get it mounted onto the power supply. Okay, so we've got it mounted on the power supply there. I'm pretty happy with that construction. That's certainly rigid enough. You can see there I've got plenty of room to mount a couple of these. So what I'm going to do, originally I was going to use the microcontroller as well as dealing with the front panel LED. I was going to use the microcontroller to control the PWM of the fan. But that's probably boiling the ocean, and as it happens, this fan is a 3-wire fan, doesn't have PWM control, just has tacho output. And I've just had a little play about with it on the power supply, and I can vary it with DC. So I've got a few of these kicking around, these are the sort of cheapo switching buck regulators. So I need one of those to generate the 5-volt supply. This has only got a 15-volt supply, so I'll generate a 5-volt supply for the video board and also for the Rubidium Frequency Standard. But I think I'll stick a second one on here as well to deal with just generating the supply voltage for the fan. I'm not going to boil the ocean too much here. Just simple and quick. I'll stick a 4-pin header with 3-pin compatibility on it, so I'll be able to change the fan in the future should I need to. And I think that's it. So I don't think I'll bother showing you this construction on video. I think it's just a waste of time. Hopefully now you've got a sense of how I'm approaching this. So far I'm about 2 hours into this, messing about, drilling holes and messing about, got the basic physical construction going, and I think once we've got there, once I've built this, got the microcontroller on there, I'm just going to stick an 8-pin socket, got that wired. I'll do a quick hand schematic of what the control microcontroller is going to be doing for the front panel control, and then I'll do a bit of a screen recording and show you building software for that very quickly, programming it and testing it on a breadboard, and we can pop that in. So I'll have all this wired ready to receive the microcontroller. I'll get this wired, get the power, test the power supply. Make sure all the DC levels are set correctly before we connect up and give this a final test. All right, so I'll go off now and wire all this up so it's all wired. See you in a minute. Right, so there's the power supply built. I'm just going to give it a test. I've used three power supplies, or three power supply modules. One's for the controlling the fan. I just thought that was easier, and also this is only a 3-wire fan, so I didn't have a PWM controllable one. I was going to drive the video board, wherever it's gone. I was going to drive the video board. Actually, I did try running them both off 15 volts, and it actually works fine. The problem is the positive 5-volt regulator actually dissipates quite a lot of heat, and there isn't really a heat sink on it, which is why it was obviously being run at 6 volts. So just for ease, I've created a separate supply so I can run those at the intended voltages. So one's going to be providing the 6.5 volts needed for the video front end. One's going to be driving the fan, and one's going to be generating 5 volts, and that just mounts here. So what I'll do, just before I mount that, we'll give it a quick test. I've got a power supply here with 15 volts output, which is what's coming out the switch mode. Okay, so with the supply on, that's ground. That's the 15 volts that will supply, that's coming directly from the switch mode. That will supply the preamps negative supply volt generator, plus 7 volts, which is what this is set to. The fan is being driven, I think I've got it set to about 7 volts, so that should spin the fan, which is running there. And then this is going to drive the Rubidium. So this is the 5 volt supply, which is being generated by the third switch mode here, and 15 volts here for the other supply. This additional connector here is the ready signal from the Rubidium. So that's connected to this chip down here, which is where the microcontroller will be, and that's the connector for the LED. Alright, so I'm going to go and connect all this up and build this so it's all ready to go, and then we'll look at the microcontroller next. Okay, so the basic system is wired now. All the wiring is done. This is what it looks like. Let's zoom in a wee bit here. I've used PTFE wire here, just because obviously it gets hot, so we have some of that lying around, so PTFE wire is probably a good thing to use. You can see the mains is wired. This earth is ready to go onto the top lid. I've made it so this has got a fairly decent fly lead. It does mean if I need to test any more of these things, it'll be relatively easy just to pop that out the side and plug it in. At least I've got a working test framework. So what I think that I was going to do, set up a test here. Just to make sure. Right, I'm going to give this a quick test. I've got the scope hooked up. I'm just going to pop that into one of the outputs in the back. Doesn't really matter. Pick any one of them. Okay, so switch it on. Fan starts, which is superb. Have a look up at the scope. There's a 10 megahertz output, and if we have a look here again, what we should see here is a 12 volt supply, a 5 volt supply. This is the ready, and this is going into pin 2 of the microcontroller. We'll take a look at that next, but what should happen is as that warms up, that should drop down to 0. Okay, there you go. It's gone down to 0.22 volts. So that's great. So that's our Rubidium frequency lock ready signal, which is visible on the. Let's just check. That is pin 2 of the microcontroller, I believe. Alright, so that's all ready to go. The last thing to put in here now is the microcontroller. Just got to plug it in. So next thing we're going to do is we're going to take a look at that firmware and see if we can work up a small program just to deal with, just so you know what I've got wired here, and I'll draw a little circuit so you can see it. But effectively we've got the ready signal coming from the Rubidium into one of its inputs. We've got the LED on one of its outputs, power and ground, that's it. We're going to program this up so it's what we're going to aim for is when we first switch it on, I want this to blink on and off, and then when it locks it, I want it going on solid. Okay, so that's what we're going to aim to do. It's a really simple piece of code, but anyway, it's all part of the project. We've done drilling, we've done filing, we've done soldering, we've done modifying video boards, we've done all sorts of stuff, so now it's time to cut a little bit of software for the project. Okay, so here's the schematic for the PIC microcontroller and how I'm using it. So first of all, this is a simple 8-pin device. It's got about a kilobyte of RAM, kilobyte of flash, 64 bytes of RAM, an internal 4 meg clock. It's got some peripherals, but I really don't need any of that, so I'm using it as a very basic microcontroller. So VDD and VSS runs at about 5 volts, can run slightly higher than that, but 5 volts anyway. And then these 6 are GPIO 0, 1, 2, 3, 4 and 5. So how I've got it wired, very simple, supply and ground. I've got a pull-up resistor on GPIO 5, which is my sense input, and that comes from the RBS ready signal. That's an active low signal from the Rubidium standard, so it's an open collector drive. So when the Rubidium is ready and locked, that signal is pulled low by the Rubidium, and that will obviously take this to a logic 0. On GPIO 2, I've got an LED. I should have had that drawn with a couple of arrows. Let's just put that in there. An LED, 150 ohm resistor to ground. That's it. It's really as simple as that. Now, in terms of construction, what I've done, I've just knocked up a little programmer here on the breadboard, and I've actually purposefully not used pins 6 and 7 and pin 4, because these are the 3 pins that you use for programming. This is master clear stroke VPP. I think this one is clock and data for the programming input. So I've left those. That means I can basically develop the software on here and test it and see the actual thing here. I've got just a simple wire connected to pin 2, which is going to simulate the RBS ready signal, so I can just move it positive, negative. So leaving it on the plus 5 volt rail will simulate the RBS warming up, and pushing it onto the 0 volt rail will actually simulate the RBS being ready, so we can develop the software from there. Okay, next up, let's actually have a look at the software and see if we can construct something really simple to make this PIC work. Okay, so I've set us up to basic project here. What I've done, I'm using MPLabX latest version. I'm also using the latest XC8 compiler. Now this is all free software, you don't actually have to pay for this. This is the software I'm using. It's the non-licensed one, so it'll generate slightly inefficient code. I'm not going to bother going through the setup in this video. If people are interested, I was thinking about doing a kind of ground zero PIC programming tutorial in C, because Arduino is great for stuff, but it's not perfect for everything, and I much prefer. I happen to know PIC microcontrollers. Anyway, I'm not going to rant on about that. Just to say, for now, I've set up the basic project for the particular device. If you come and look in here, you can see I've chosen the PIC 12F675. I'm using ICD3, which I've got hooked up to the breadboard, as you saw earlier on. And I've set up a basic C file, nothing complicated here, just include xc.h. These are configuration bits. You can generate them down here just by setting the configurations and then generate source code, and it'll just generate them, so you can pick them up and just paste them straight into your code. It's very simple. So what I've got set up here, I'm going to run the internal oscillator, and I want GPIO on GP4 and GP5. Don't want a watchdog timer, don't want a power up timer. I want to disable master clear reset pin. I want GP3 to also be an input. I'm also going to turn off brownout reset, don't need that either, and I'm not going to protect the code. It's really nothing in here complicated. So I've also added a couple of comments here. RBS ready, so those are my two input signals, and it's always a good idea to define the actual frequency the clock's running at. It just means that the delay function that we're going to use will actually make sense when we use some numbers on it rather than just randomly making stuff up. Okay, so with that in there, just do a quick sanity check, a quick clean and build, just to make sure that we get a nice clean output. There you can see, and you can see much RAM and how much flash memory we've used, so we've got plenty of space. Okay, so what do we do first? So the first thing to do, or at least I like to do, is define the so the first thing I like to do is define the input and output pins. So so the first one is going to be the RBS ready signal, and that's on GPIO 5, if you recall from the schematic. So just define that one there, and the next one is the power LED, and that's on GPIO 2 from what I 2, wasn't it? Okay, so once we've got that, it just means that instead of having to remember that, I can refer to these as RBS ready, and you'll see why that makes sense here. So now this is going to be such a simple program that there's no need to generate any interrupts or do anything else with, but we're basically going to run an infinite loop, and we're going to check the status and act. First things first though, we've got to set some things up on this chip. I have made a note of these because I never remember them. You normally have to refer to the data sheet and mess about a bit. Anyway, by default in this chip, LED con, the certain inputs are set to analog inputs rather than digital inputs, and so we just want to turn that off. Okay, so I'm going to turn off. And it's always a good idea, just make comments and remind yourself what you're doing. Next thing we want to do is make sure that all of the analog inputs are turned off and they're all converted, and they're all, so all of your inputs end up being digital inputs rather than analog inputs. So next thing we want to do is there's an internal voltage reference. It doesn't really matter, but just for completeness, I'm just going to turn it off because we don't need it. This chip also has a comparator on a couple of the inputs, GPIO 0, 1 and 2. We need to turn those off. I basically disable the comparator on those as well. So the comparator configuration, again, you'll get all this out of the data sheet. You need to set the first 3 bits to 1 to do that. Okay, so we've got that. The next thing we need to do now is set up our I/O pins to be the inputs and outputs respectively, to make sure they're going to work. Okay, so that's done on a PIC. Most PICs typically that's done on the TRIS I/O register. Now, so if you recall from here, we've said that RBS ready is on GPIO 5, and that's an input, and power LED is on GPIO 2. So TRSI 2 We want to set that to 0, making it an output. And we want to, a bit of a shortcut there, set GPIO 5 to an input. Oh, I can't type, it's getting late. Right, okay, so that's our basic setup. So that should allow us now to write a program. So I think the program is going to be really simple. There's absolutely nothing to this at all. We're going to go into an infinite while loop, so while 1. All that's going to do is it's going to go around in here forever. And then the first thing we're going to do is inside this loop I'm going to say if RBS ready equals to 0. You remember the Rubidium input pin will be pulled low when it's actually stable and locked. So all I'm going to do here, power LED. We just go, so if it's stable and locked, we just want the power LED to be turned on. Simple as that. And now of course it'll keep on coming in here and turning the LED on, but that doesn't really matter because it'll be on already, so turning it on really just doesn't have any effect, so that's fine. Else, okay, so if it's not ready, what we're going to do is we want to flash the LED. So what we're going to do here is we're going to turn turn the power LED on. Then I'm going to, no I'm not, so let's not do that. Let's say if power LED is off, there we go. Turn it on. Else. Turn it off. So that's going to give us an alternate toggle. Of course, that's going to go at lightning speed, so you'll never see that. You'll probably just see half a dim thing here. So what I'm then going to do is just do a delay. Now this delay function will delay for however many microseconds we specify. So let's say 400,000 microseconds, which is 400 milliseconds. That's just under half of 1 second. So that'll effectively, so if we just follow that logic through now, you can see what's going to happen. It's going to come into this while loop. It's going to check the input status of ready. If it's low, if there's a 0 on the input, it will just light the LED. If it's high, it will turn the LED on or off, depending on, it'll make the LED its complement, and then it'll delay for 400 milliseconds. Then it'll do the whole thing all over again. So the effect there is if this is 0, the LED will be on all the time. If this is 1, the LED will flash on, off, alternate. Now, and that's pretty much all we need. Now just make sure that builds okay. So I think that's it. I think that's the entire firmware. Really simple, really rudimentary, nothing complex here. Now one of the things I quite like in status LEDs is for the on time to be shorter than the off time. So I'm just going to tweak that around a little bit. What I'm going to do is I'm going to keep the off time to 400 milliseconds, but I'm going to make the on time let me see, a quarter of that. So let's say 100 milliseconds. There you go, and that's how you achieve that. Quite simple. Okay, so I'm just going to power up the microcontroller now. You'll probably hear a little bit of fan noise. Get 5 volts on it. I'm going to see if I can program this chip and see if that actually works, and then I'll switch back over to the camera, and we should be able to see the actual code that we've just written work. Okay. So to program the chip, once you've got connected, simply make and program device, or that's the option I always use. That just forces a remake, switches over to the programmer. Okay, and we're programmed, and I now have a flashing LED. Okay, I'll finish up the recording here, and I'll switch over to the camera and show you the actual that code actually working in practice. Okay, so here we go. Here's the microcontroller running the code that we've just written. You can see the LEDs flashing here. I'm going to take the RBS ready signal. I'm going to pull it low, and there you get with nice steady state LED. So yeah, that's it. It's really that simple, nothing complicated. You know, back in the day, I would have probably had to use something like a 555 timer to do something like this, and messed about and had discrete components and so on. One of the great things about modern day microcontrollers, especially these small ones, is they're really convenient for doing this sort of stuff. They're small, they're cheap, they're fast to construct. You know, they've got built-in oscillators and all kinds of stuff, and as you can see, we're under full software control. All right, the next thing to do is to plug that into our RBS, power it up, our actual Rubidium Frequency Standard circuit that we built, and see if this actually works in place. Okay, so I'm just going to put this this chip just in here. Hopefully this is all wired up as it should be. This is the chip we just programmed. I'll just lift it out of the breadboard. Okay. So what we're expecting now when we turn this on, this LED should be blinking, and then as soon as it gets ready, there we go. As soon as it gets ready, it should go on solid. So I'll leave this on, and I'll speed up the video so you don't have to watch through the pain. I think it takes about 2 or 3 minutes. The scope, just while we're looking at that, the scope is again showing us the output there, so we can see the output from the amplifier. Okay, and then assuming this works, that's really it. It's job done. Everything's built. I'm just going to reconstruct the case and put it back together. Hey, and there we go. So we have a lock. So that's it. Great. That's all working. Let's have a quick final look at the inside of the project. I think it's a reasonably neat and tidy job. It's built to be robust. So hopefully it should last a while. Probably take a bit of a battering. There you go. That's the back of it. You can see the fan. Shame about that overbore on the fan, but that's, as I say, it's not the end of the world. Right, so I'll just put all the casing back together now. Okay, so there we have it, all done. It was about 4.5 hours elapsed time. I did stop and have something to eat, and you know, general, had a couple of visitors and that kind of stuff. But yeah, about 4.5 hours of messing about to get this. So overall, I'm pretty chuffed with that. Pretty simple. Nothing ingenious in here. It was simply integrating a whole bunch of different parts. Just going back to the original discussion, though, I think it is important that when you're, you know, if you're going to make use of something, you do need to produce it in a way that it can be used just like any other piece of professional kit. Even though you make it yourself, and you know, I haven't sprayed the front or, you know, tried to put logos on it or even labelled up the back actually, but I know exactly what it is and what it does. And that's good enough. But the point is, it's safe. It's correctly wired. You know, double pole hard switch to isolate the mains. Properly earth bonded inside. You know, so, and it's got a reputable, good quality switch mode power supply. So what more can you ask for? This is a pretty good bit of kit. Anyway, that's it. So if you enjoyed the video, if you thought it was interesting, please give it a thumbs up, and I'll catch you next time.